Thank you. It's a real pleasure to be here in really my first face-to-face conference since the beginning of the pandemic. So this is a very exciting time for me, and it's doubly exciting to have it held in Seoul, one of my favorite cities, and to really see so many friendly faces. So for those of you who don't know me, I'm one of the professors at Nanyang Technological University, and what I do is I lead this group called the Quantum and Complexity Science Initiative, where we have a lot of interdisciplinary talent looking at how can we take techniques that the mathematics used to understand and study complex systems and complex processes, and see if we can translate them into sort of the quantum computers and see whether quantum technologies can give us advantage. And today, what I want to tell you is about our recent pandemic advances, where we've been thinking about how to look at how these ideas of intelligent agents that adapt to their complex environments, and see whether these agents, if we translated these agents so that they process quantum rather than classical information, that they will have kind of a processing advantage. Now, before I go any further, a quick disclaimer. There is not going to be too much optical quantum technologies in this talk, but hopefully by the end, I'll have a few slides to say what quantum technologies, what optical technologies may be really suited for in terms of these algorithms. So let us begin. So when we think about agents, usually if we look up agents online, what typically comes up is more from the computer science side. So agents are used for modeling sort of biological systems. Say we think about them as, say, a predator chasing prey. Or more on the engineering side, we use these ideas of autonomous agents to think about, say, autonomous vehicles, basically machines that we build so that they sense the environment, and based on what they sense in the environment, adjust themselves so that they can, say, for example, safely drive our traffic networks. But it's always good to keep in mind that the first agents did not actually come from the realm of computer science, but really the realm of physicists. And probably the first scientific study of agents was captured in the thermodynamics, starting centuries ago, when people were trying to understand this paradox of Maxwell's demon. And as we know, Maxwell's demon seemed to suggest that we could violate the second law of thermodynamics by monitoring sort of the cold particles on one side of this compartment, and if, depending on their temperature, whether to let them go onto the other side. And it wasn't until we understood these agents from a physical perspective that we could resolve this apparent paradox. And so the idea of agents is really deeply rooted in our understanding of physics. And today, in terms of quantum technologies and the construction of quantum computers, the ideas of sort of using these agents have come into prominence again in the sort of understanding of the suppression of non-Markovian noise. So when we build these quantum computers, we find that whenever we sort of look at the noise profile of a gate, it often depends on what gates we have applied previously. The environment isn't this Markovian object that just forgets, it remembers what we have done before. And to be able to sort of counteract that, we also need to remember what we have done before. And so roughly what an agent is an entity that captures past experiences and takes future actions based on those past experiences. And in doing so, such an agent is able to adapt to complex environments. Now, a typical picture of an agent is put forth like this. We have sort of the input stimuli. We have, this is actually just a mouse. Sorry about that. Let me use the proper mouse here. So we have the input stimuli here, which is basically what the agent receives from the environment. And depending on what the agent receives, the agent will decide to take various output actions. And the way the agent makes that decision process is that internal to the agent, there's some sort of memory. And the agent's action is solely determined by what he receives as input and what is the state of its current memory. And the function that sort of decides what action to take is often termed the policy, kind of how do I select the next action based on my previous knowledge. And I have a kind of a 3-year-old daughter here, and you can really see this process in biological entities. So as she's growing up, she's really prodding things, trying to determine the causal relationships, and based on this, formulating new actions. And this is really what sort of the picture of an agent tries to capture. Now, the key thing here is that the agent has this memory, and this memory is important. Agents can do better with memory, and this memory is absolutely needed once if we want to take advantage or adapt to complex settings. And one of the first sort of illustrations I have here is from this movie Ocean's 11 on the game of blackjack. So if any of you have frequented casinos, then you'll know that blackjack is one of the most popular card games. And if we just played in a memoryless strategy, so that's to say that we just look at the cards that we get and make a decision purely on the cards that we see at this particular time, then we will never be able to beat the house. But there are card counting strategies that by looking at what cards have played before, we can adjust our strategy so that we actually have an edge over the house. And so having this memory allows us to adapt to our strategies and really gain this competitive flavor. And in this case, it's the simplest strategy of that sort is just to count the number of high cards. And based on that, sort of decide whether or not we will sort of place a higher bet or no bets at all. And indeed, if you do this too well, you kind of get kicked out of the casino, as some of the students at MIT found a few decades ago. Now, another illustration, which is a bit easier to sort of find the upper boundaries, is this classic game of Pawn. So I guess most of us are probably a bit too young to have played this at our homes, but this was one of the first games that was available on the first game console, the Atari, and it's a very simple game. Basic idea is a player has a paddle, and there's a ball that's bouncing, and it's just bouncing diagonally on the screen. There's only 4 possible directions it can go, and the paddle kind of, you move it up and down so that you hit that ball. And if we think about an agent playing this game, then the input stimuli would be kind of the entire state of the screen at each time step. So that's what the agent sees at each time step. And based on this, and the agent's memory, he forms a particular action, a particular policy of what he wants to do next. And here the action is very simple. It's just up or down. There's only 2 possibilities. And then in this way, the goal of the game, of course, is keep hitting that ball and make sure that it doesn't go out of bounds. Now, one thing to note is, as with all these agents, the policy does stay the same at every time step. So the agent always behaves the same way, statistically behaves the same way, as long as he receives the same stimuli and he has the same state of memory. So the agent's adaptive behavior is totally controlled by the memory state. Now, in this scenario, it looks like a fairly simple game. The environment looks essentially Markovian. It's basically the dynamics of ball. But memory still helps. And if we think about it, how does memory help? Is that what we observe here is just the position of the ball every time step. We don't observe the momentum. So the momentum is hidden from us unless we recall information about what happened prior. And if we think about how much memory we need, in this case, it's actually fairly easy to bound analytically, because that ball only has 4 possible directions it can go. It only moves diagonally on the screen, so top left, top right, bottom left, bottom right. So there's only 4 states. So if coupled with our observations, we remember those 4 states, requiring a maximum of 2 bits of memory, then we would have had tracked everything and would be, in principle, be able to come up with the optimal strategy. In fact, actually, you only need 1 bit of information, because it turns out that the best strategy is just follow the ball, no matter if it's going away from you or towards you. As long as your paddle keeps in sync vertically with the ball, we're fine. So actually, 1 bit of memory is required. But this kind of illustrates that there's this value to memory, even in sort of these very simple games. And also kind of illustrates that this gives us a notion of the complexity of our environment. So more complex environment, then typically we will need more memory to be able to track it. And indeed, there's this thing called the principle of requisite variety in cybernetics, which sort of talks about the optimal strategy for sort of adapting to a complex environment is at least as complex as the environment itself. So there's this idea that intrinsically there's a complexity outside in that environment, and to adapt to it, we're going to need memory to be able to capture those correlations. I should have 2 clarifications here. One is that this is really solely a thing about memory, how much information we track from the past to the future. And this notion of complexity doesn't necessarily capture the complexity of executing this policy. So under this sort of notion, the game of Baduk, for example, is very, very complex, but it's considered fairly simple in this setting, because all the complexity is in building the circuit, and the memory that we don't actually need to track any memory here because the environment is completely known to us. It's a wholly observed environment. But nevertheless, in general, if we have the more complex our memory, the more states we have to track in the memory, in general, the more complex the policy is as well. And indeed, the dimensions of the memory bounds the dimensions of this policy here. And so it gives an upper bound to, well, how many gates we need to execute this policy P. So now in industry, sort of here was a paper in Facebook made by sort of the research at Facebook. They are interested in the complexity of these games and how much we can simplify these things. So there was this paper here on learning the causal representations of partially observed environments where they just took a bunch of Atari games from the 70s and benchmarked them in how complex an agent needs to be to play almost optimally in these games. And it's all very numerical, so there's a lot of error involved, but you can sort of see that Asteroids is considered a very complex game, probably because there's lots of rocks flying about and you need to track the momentum of all these rocks, whereas games like Pong is remarkably simple. You can see they have a lot of error here. It's -2 ± -6. But that's, I guess, numerical studies. So now what we're interested in, though, as I mentioned, is, well, can quantum agents help? What happens if we take that memory and we make it quantum mechanical? And to do this, we're going to have to formulate a little bit more mathematics. The first thing is we need to define what we mean by help and what we mean by executing the right strategy. So we need to define what we mean first of a strategy. And this sort of in the classical community can be sort of described using the language of complexity science or computational mechanics. And the basic idea is that you can describe any sort of strategy by a family of stochastic processes. One stochastic process for each possible input distribution. So this is a very large space. I mean, a single probability distribution stochastic process is already, you know, an exponentially large probability vector depending on its temporal Markov order. But if you have like an infinite family of them, it's in general very tough to informationally describe. But in principle, mathematically, we can write it in this form. And the idea of a strategy, the agent that executes the right strategy is basically an agent that is able to take the past information of what it observed. So there's some function that maps the entire past, the past inputs and the past outputs, into the state of the memory so that given any possible future input, it can still come up with the right statistical behavior, regardless of what future input. It has to be mentally prepared for every possibility that it can see in the future. And the amount of information it needs to track to do so is basically the amount that it has to retain in that channel that we described previously. And so our query then is, okay, can we kind of encode that past in quantum states so that we can track less information and still be able to execute the exact same statistically faithful strategic behavior? And this is a general, very complex question. So let us start with a simple example. So here is inspired by the movie Blade Runner. We've got sort of a computer that's trying to pretend to be human, but let's make the problem very easy. To succeed, that computer just has to sort of exhibit the following behavior. So every round, he is asked one of two possible questions. Do you like electric sheep, or are you human? Z equals 0 and Z equals 1. And the agent is asked to behave in this way. If he is asked the same question consecutively twice, his answer must be consistent, so it must agree with the previous answers given. And the second is that if he is asked a different question, then his answer to the different question should be statistically random. And so let's see how we can satisfy this classically. So using a classical machine, we realize that there are two elements of the past that really matters. One is which question was asked, and two was what answer the agent gave. So an agent trying to replicate this needs to kind of track, have a memory with 4 discrete states, or 2 bits of information, so that he could track these 2 bits of information. And in doing so, you can draw sort of a finite state machine that is able to give exactly the right behavior. And now, what if we go to the quantum regime, though? Well, it turns out that this problem was kind of engineered, reverse engineered, so that quantum machines can help particularly easily. And if we think carefully, well, asking the two questions is like measuring the two complementary bases of a qubit. So if we take a qubit, then we measure it twice in the z basis. It's going to give us consistent answers. If we measure in the x followed by z, or the z followed by x, then the answer is going to be random, just like the Stern-Gerlach experiment. And so if we were to store the states of the agent in these four states, sort of up, down, plus, and minus, then we are able to replicate the behavior by basically choosing to measure in x or z basis depending on which question was asked. And now we've reduced that 2 bits of classical data into 1 qubit of information that we need to track. And so we can see that at least in one instance here, a quantum agent is able to do something with smaller memory than a classical one. So if we sort of had this memory constraint scenario, we said, okay, we only have 1 bit of memory, 1 qubit of memory, then the classical agent is not going to be able to do very well in this environment, whereas the quantum agent would be able to perform optimally. And so let's see where the source of that advantage is. So where did it come from? And the key thing here is that if we imagine that we had 2 different paths, so this is path A, which is basically someone's asked, do you like sheep? And the answer was yes. The other cases, they asked a different question, and he also answered yes. And and imagine that we have 2 agents that experience these 2 different paths. And us as an interrogator, our goal is to question the agent subsequently to know which of the 2 different paths the agent experienced. Was it path A or was it path B? And the question is, can we perfectly retrodict which path that agent experienced depending on a sequence of future questions? And in this case, the answer would be no. And the reason for it is quite simple. It's because we can see that we were able to represent this agent quantum mechanically, if we wanted to. And if we were able to perfectly distinguish which path the agent came from, we'll be able to perfectly distinguish between the plus state and the 0 state in violation of the uncertainty principle. So the fact that the quantum agent exists here really tells us that there's no way for us to be able to retrodict which path we come from by interrogating this agent. Otherwise, we'd be able to distinguish non-distinguishable states. And but if we look at a classical agent operating on this, well, the classical agent has assigned distinguishable states. So 1 bit, that's either 0 or 1, to these 2 different paths. So in a sense, that classical agent is assigning more information into its memory, or taking more information of the past into memory than what it can ever exhibit in the future. Some of that information is lost as it sort of proceeds to execute the future part of that strategy. And so one can form an information theoretic argument, which is to say that here is all the information that the agent tracks about the past. Here's all the information about the past the agent could track about the past. Here's all the information that's relevant to the future. And the information that the agent actually stores about the past is sort of recorded here in this sort of shaded box. And what happens with classical agents is, in general, is that they are always tracking some information of the past that is never reflected in the future. And this we can think about as a sort of causal or information waste. And it's that waste that can be reduced in the quantum mechanical framework. And indeed, in a series of publications here, what we were able to show was that whenever there's any of this causal waste involved, then you can always systematically, or we have a method to systematically design a quantum agent that tracks less information than the classical agent in the sense of information entropy. And the form of that agent, that quantum agent, very much looks like this. It's basically you have a quantum memory that comes through here. At every round, it's the same unitary interaction. That's basically the quantum version of that policy. The input can be sort of stored in terms of a quantum state. And we're also feeding some blank acyla. Some of it is erased. The rest comes out as output that, when measured in the computational basis, gives you the statistical behavior of the agent at that time step. That measurement automatically collapses the memory into the correct state for the next strategy. Or if it's not measured, then you get an agent performing a superposition of possible strategies depending on possible inputs. And so we end up with one of these machines. And the next result that we identified was that there is a scaling advantage as well. And the specific scenario we looked at was we imagined that in the environment there was some continuous parameter lambdas. And the optimal strategy is a function of this continuous variable parameter lambda. So basically, the more precisely we know this lambda, then the closer to the perfect strategy we can execute. And this lambda is a hidden variable in the environment in the sense that the agent has to track it to be able to execute that strategy. And so if we had a classical agent, the typical way one would do that is to track that in some sort of floating point number representation. So the more bits we assign to that floating point number, the more accurate we will be. And so as we increase our precision, of course, we also increase the amount of memory that we need to track. And what we can show is that there exists some criteria, mainly about the dependence of the strategy on this parameter being sufficiently continuous, but too mathematical to go through in this talk. But it's a kind of a condition that we can check. And as long as the agent satisfies that strategy, then a quantum agent is able to execute the perfect strategy with finite memory. So he doesn't have to track that parameter lambda classically. That lambda can be written in terms of in quantum memory, and that quantum memory, the entropy of that quantum memory can stay bounded, and the agent is still able to execute the statistically perfect strategy. And of course, if we don't demand perfection, then the agent is able to execute the strategy to a better fidelity. And so one of the special cases of that is a resettable stochastic clock. So here we imagine that we have a scenario where our agent is fairly simple. It's like a stopwatch. So at every time step, there's either we can let that watch, the agent either keeps going and keeps counting time, or someone presses a button and resets the stopwatch back to 0. And the idea is that this agent is it's a finite precision clock. So instead of having a perfect Dirac delta distribution between ticks, there's some stochastic distribution, as with any realistic clock. And if those of you familiar with, say, the results of Renat and Renner, you know that we already know that there is some sort of memory advantage with tracking time for quantum mechanically, and in the sense that a quantum clock is able to track time more efficiently. And in terms of this memory, we can kind of formalize that to a generic class of renewal processes, so where this weighting distribution can be anything that is continuous. And what we can see is that there's a memory advantage. Classically, as we require more and more memory, as we try to replicate this behavior to higher and higher positions, but quantum mechanically, it actually saturates at some finite point. And so that comes up with a sort of a rough summary of some few of the take-home messages. One is that in a lot of cases, people really do care about this memory in terms of it's a measure of how much information we have to track about a complex environment to be able to replicate sort of the good strategies that survive in that environment. And generally, the more non-Markovian environment is, the more its past, its future depends on its past, the more memory we have to track to be able to sort of better adapt to the environment. And it turns out that when we have quantum agents, they have advantage in adapting to these environments, as long as we have a bounded memory. If our memory resource is unbounded, then we can, in principle, execute any input-output strategy. So if there's no constraint on memory at all, then quantum and classical behaves roughly the same. But as soon as we put in a memory constraint, then the quantum agents can access a more complex repertoire of strategies than what a classical agent is able to. And what we can show is that this advantage does scale, that there are many situations where the minimal memory requirements for executing the theoretical optimal strategy is significantly reduced or scales in a more favorable manner for quantum agents than classical ones. And in the last kind of 3 or 4 minutes, I just want to quickly talk about some of the interesting possibilities, some of the open questions. And now the most immediate open questions that we're currently tackling is we want to start taking these agents and start sort of seeing what they can do. Maybe seeing whether they can outplace a classical agent in a game of Space Invaders with finite memory. This is, I think, a really fun project for sort of students and stuff, and so it's something that we're beginning to tackle. We've got some computer science students that are coming in to look at these things, where we want to start learning these agents. So currently we are constructing these agents by hand. This is an analytical way to construct it, but it depends on knowing what the optimal strategy is. And in most scenarios, we don't really know what the optimal strategy is. We have to learn that. So classically, that's often done by reinforcement learning. So we want to see, can we use reinforcement learning methods to learn these quantum agents as well? And finally, going back to where agents originally started was thermodynamics. So we want to go back, close that loop, and see, okay, what can these quantum-enhanced Maxwell's demons do for us in terms of understanding or harvesting energy from non-Markovian environments, or what are the thermodynamic costs of executing complex strategies? And for those of you who will be listening to my next talk in Kiosk, hopefully sometime next week, I'll be talking a little bit more about these ideas. And the next thing, going back, is this is a session on optical technologies. I should probably make a mention on sort of that we are pushing towards potential optimal implementations. And what we have done so far is kind of an agent with only a single possible input at each time step. So an agent that has a single input is just a model. It just executes, generates a single stochastic process. And we were able to sort of do that and show quantum advantages already using the optimal regime. And the trick with these things is to encode qubits in time, the time-bend degree of freedom, which is very nice because it allows you to sort of generate a pulse of photons and have photons interact with their previous ones to create a correlations in time. And it'd be great to see if this can be done sort of in an integrated circuit manner, whereby we have a single circuit and we recurrently interact photons encoding time-bend degrees of freedom to be able to sort of build up an agent that sort of adapts things in time. Now, I'm running out of time here, so I won't say too much, except that there is a broader perspective out there. With that broader perspective, we can think about not just the agent having a quantum policy, but also the inputs and outputs being quantum mechanical as well. And we already have instances of that in optics. That's quantum illumination and quantum sensing, where the agent stores memory information in quantum memory and sends out a probe in terms of entangling photons. That allows us to detect things in an enhanced manner. So it'd be great to integrate that with our quantum agents so we can sense the environment quantum mechanically as well as process the data. And once we have that, we end up with a general quantum comb for understanding quantum agents, where agent is continuously interacting with the environment. And we already have some interesting results in that about temporal uncertainty principles. But I will stop there, and thank you very much. And here's some references if you're interested in reading up on these. Thank you.
Thank you, Professor Gu, for the inspiring talk. Let's have some questions. Do you have any? No?
Yeah.
Yeah. You have any question?
Oh, yeah.
Okay.
I have a silly question. Anyways, thank you very much for the nice talk. Can you use this for a practical application, like to characterize noise or whatever? I think because your title implies that there is a to understand or to adapt the complex environment. So environment causes noise.
Yes.
So is there any clue you can find more easily with your quantum agent?
Yes, so currently we're looking at two different applications. One is in sort of a signal processing or signal analysis. So where we have data coming in terms of a data stream, and there are words in that data stream, and we want to classify what those words are. Now, so this is the typical problem in sort of, say if someone's speaking to you, and then we need an algorithm to be able to group these words and be able to classify them. Now, sometimes these words can be they look very similar, except their correlations in time. So one has to track a lot of memory to be able to sort of distinguish these things. And we're looking at sort of very efficient quantum machines to be able to distinguish sort of this sort of temporal data. And some of the potential applications of that is actually, say, in distinguishing regimes in financial analytics, where they have sort of high-risk regimes and low-risk regimes, and we want to find ways of being able to detect these regime changes faster. So that's one area of applications, and we've got this grant with one of the major banks in Singapore to look at these. The other area that we're looking at is more towards sort of understanding a quantum environment, and so far we're looking at it in terms of harvesting free energy from a non-Markovian sort of a quantum correlation. So we imagine that our environment is highly non-Markovian, and we are trying to monitor to be able to better predict what will happen next for the purpose of energy harvesting. But I believe that similar techniques can be adapted to understanding and suppressing error as well, because harvesting energy very much requires the same notions of understanding what will happen next. And certainly we're interested in sort of adapting this to suppressing non-Markovian noise, but we haven't begun looking in that direction yet.